Okay, good morning. So let me continue the lesson. And of course, I updated the PDF file because I am just writing it when we are continuing the course. So then I will not change anything. So you can see that the date, it has been edited, for example, today. So it means that even though everything seems the same, but I have added something to the PDF file. So I will update the PDF file as we continue. Okay. So one thing we learned about a very basic ideas of matrix theory, and then so we learned that in general we want to write a matrix m by n, and I told you that always m refers to the number of rows and n refers to the number of columns. So in this case, generally we write it like this. We write little h shows it from here, and then I equate it with two subscripts I, j, and I is the row number or row index, and j is the column index. And then I write m by n. So then we learn that if you want, this means when you see this symbol, you need to imagine that you have something like this, A11, A12. Let me write some of them, A13, and it continues to A1, what? In this case, n, because you have n columns. And then you go to the second row, A21, A22, A23, and then you continue until A2n. And then you can continue this list, and you start with AM1, because now you are on the last row, but it contains m rows, so it starts with M1, and then you M2, M3, and then you continue mn finally. Yeah, so that is what you need to imagine when you see such a symbol. Okay. But if you remember, I was introducing different terminologies so that we know what we are talking about. So the last thing that I was talking about mainly was the notion of a square matrix. So let me make it 3 by 3 to save some time. So assume that you have a square matrix. It doesn't matter what type of square matrix it is. 1 by 1 is just a number, 2 by 2, 3 by 3, etc. So let me just pick a 3 by 3. 1, 1, 1, 2, 1, 3, and then you have A21, A22, A23, and then you have A31, A32, A33. Okay, so I told you that if you have a square matrix, then you can talk about diagonals. Yes, main diagonal and a minor diagonal, or major diagonal, minor diagonal. So what we say is the entries here are called the entries on the main diagonal. Major diagonal, yes. And the entries, so by the way, that's good to know. How can you recognize that an entry is on the main diagonal if it is a square matrix? Yes?
The three numbers are the same.
Their indices are both the same. So you see 1, 1, 2, 2, 3, 3. Yes? And by the way, I told you that even in rectangles, we can talk about diagonals, but if I have a rectangular matrix, the notion of diagonal is not defined at all. So the notion of diagonal is only defined for a square matrix. Okay, so here, let me just write here. If I want to have you, it's good to have a picture in mind. So if I draw this line, I can write it I equals to j. Yes? So what happens on this part? I index is smaller than the j index. So here I index is smaller than the j index. So you see here, whenever you look at an entry above, by the way, these are called the entries above the diagonal, main diagonal. So every one has the row index smaller than the j index, its corresponding j index. And that is clear that here, this is this other situation. Yes? But what can I write something? Can I write something similar? It's usually this is the only important one. Minor diagonal is not that important in matrix theory, but let us also write something here. If I want to write a property on this green line, can you discover the pattern? So here I have A13, here I have A2 by 2, and here I have, sorry, A22, A31. Oh, okay, so what is the pattern? Of course, I am just telling you the pattern, but you can convince yourself that is also true for the stronger case. So what happens here, the sum of these two indices are always the same number. So here, if you add them, it becomes 4. If you add them, becomes 4. If you add them, become 4. And what is 4 here? Can you tell me? So do you think that if I have a 4 by 4 matrix, how this will change? If I look at the 4 by 4 matrix and I go here, and then probably, hopefully, you can convince yourself that still I plus j is a constant number. But what constant number do you think? Yes?
5.
5. One more than the order. Yes? Here it was 3 by 3. It was 4 now. If you go to 4 by 4, it is not hard to see that it becomes 5. So in principle, I would say that I plus j is equal to the order plus 1. Assuming that your matrix, let me write here. So your matrix is n by n. I have written everything in the PDF file, so that is the content of the remark here. Yes?
So how can you draw a line in a 4 by 4?
No, I didn't draw that. I'm trying to motivate you. If you want, you need to sit down, try to convince yourself that this is in general true. Okay, these are very simple things, so I don't want to actually go through them. So for example, here, if I have to also turn this on. So here what I have written here. So you see, this is the content of this remark. So main diagonal, by the way, I told you before, this is not a misprint. In mathematics, IFF means if and only if. Lies above the main diagonal, this, below the main diagonal, this. And I also talked about the minor diagonal, so we have this condition. And it is not very hard to convince yourself if it lies above the minor, this sum should be less than n plus 1, and if it is below the minor, this sum should be larger than that one. Yes?
Yes.
Is that clear? Okay. So now we need another terminology here. So the terminology which is very important in matrix theory is that from now on I concentrate on square matrices. These are the most important matrices that we are working on. So we can talk about triangular matrices. And we have two of them. Upper triangular and then I have lower triangular. So these are important in matrix theory. And again, a square matrix is called upper triangular if you have this situation. So here is your main diagonal. When you say it is upper triangular, it means everything here is 0. And so this is you might, so be careful. This adjective upper refers to possibly non-zero ones, not the 0 ones. So if all the entries below the main diagonal is 0, then the matrix is called an upper triangular matrix. So this is upper triangular.
Why?
Pardon?
Why? So
There is no why. When I define something, my name is Babak, you cannot ask why, I don't know why. Yes, that's a name that we give to this one. You can ask, I don't know why this is the convention, I'm just defining it.
shouldn't that be the lower triangle?
No, because usually we don't care about 0 part, we care about the non-zero part. So this is why it's a better name, even though it seems a little bit strange when I define it. But by the way, in mathematics, when I define something, there is no why question. You might ask what was the motivation that they have named them in this way, but I don't have to address this question in mathematics. So upper triangular, yes, do you have questions? Yes?
Yeah, so it's still possible for entries above to be.
Yeah, I will
to
talk
be
about
zero.
that, but you also, yeah.
They can be zero.
Yes,
But
yes.
the only thing is that it's a guarantee.
Yeah, we have to care. We just don't look at this part and look at this part. If all of them are zero, we say it's upper triangle.
Okay.
Yeah, exactly. I will also talk about that. But in this case, you can probably understand what is going on. So the lower triangular matrix is something like this, yes? So again, you consider the main diagonal. You don't care about what is happening on the diagonal and below the diagonal. What you care is that everything here is zero. Yes, that's called a lower triangular. Yes, so that is something that you need to know. So if I want to define this mathematically, not using these diagrams, how do you say that? So if I assume that A is my matrix Aij n by n, because if it is not n by n, I cannot talk about triangularity of the matrix. This matrix should be a square matrix, then I am allowed to ask you if this is upper triangular or lower triangular or neither. Yes. So if you see what happens, A is an upper triangular matrix if and only if what happens, if and only if Aij is 0 for upper triangular, this part should be 0, but this part means I greater than j. So this is a mathematical way of defining an upper triangular matrix, and then I can say A is a lower triangular if and only if Aij is 0 for I less than j. That is the definition, mathematical definition of upper triangular and lower triangular matrix, which is actually clear from the context. Okay. So let us go here now. So you see the following examples are upper triangular matrices, and as you see, Rocco, so actually I have tried to address that one here. So this is upper triangular because if you look below this main diagonal, it is 0. This is also an upper triangular matrix, but this was an order 2, this is order 3. If you look below this main diagonal, every entry is 0. And the same thing happens here. You see, even though I have a 0 on the main diagonal, but I don't care about that. I just look below the main diagonal and you see that everything is 0. So here also the same thing. I have a bunch of zeros also above, but it doesn't matter. What matters is that whatever I have below is 0. And then probably these are two extreme cases. So this matrix is also an upper triangular matrix, this E. Because if you look below, everything is 0, even though everything above is also 0, and the same thing here. So both of them are upper triangular matrices. But of course, you can easily understand what can I say more about E and F?
They're also lower.
They're also lower. Yes? So is that clear? That was your question, and I think so we have addressed it here. So this is something that you can easily convince. Is there any questions here? So it is these are definitions. So if you don't mind, let me just wait for you to solve this problem for me. I mean, these are so simple. I don't know how to design questions that are a little bit hard to solve or interesting. But I mean, this is good to try to solve that problem. So I will wait for you a little bit. Please try to do example 1.24. Yes, please.
Can we go to the bathroom?
Yes, of course. We go here. No, let me pause the video. Okay, so could you solve the problem? So let me write it down here. So it is mentioned in the problem that A is a 3 by 3 matrix, yes? And then the entries are defined in this way. It is defined to be alpha squared minus 3 alpha times j, j is the column index, plus 2j squared, if I is greater than j, and it is defined to be 2I plus j if I is less than or equal to j, yes? And then we want to fine-tune this alpha so that this matrix turns into an upper triangular matrix. And whatever you see, it's on the board, yes? And matrix A is an upper triangular matrix if and only if aij is 0 for all I greater than j. So it is clear that this is not relevant to our problem here, because we want to make it an upper triangular matrix, and then I am always thinking about the indices, so the row index be greater than the column index. So I need to consider this one. But this is a 3 by 3 matrix, so this means that these three numbers should be 0. These three numbers should be 0, yes? Because I want to make it an upper triangular matrix. So this means that A21 should be 0, A31 should also be 0, and A32 should also be equal to 0. But let me try to write this down. A21, I is 2, j is 1. It satisfies this condition, so I have to go here and replace I and j with 2 and 1. But there are no i's here, so I have to just replace j with 1. Then it becomes alpha squared minus 3 alpha plus 2. This should be equal to 0. That's a very simple quadratic equation. PQ or ABC, or even simpler here in this case, is factorization. It's very simple. I need two numbers whose sum is minus 3 and the product is 2. What are those numbers? It's minus 1 and minus 2. Is that right? Yes. Minus 1 minus 2 is minus 3. If I add them, minus 1 minus 2, it is positive 2 if I multiply them. So that is the factorized form of this, equals to 0. So it will give me two possible answers. Either alpha is 1, or, I use this symbol for or, alpha is 2. But for the time being, this is important. If you stop here, is it finished or not? Because it only guarantees you that A21 is 0. And how many options are available to make this 0? 2 options. Either you can choose alpha equals to 1 or equal to 2. But we also have 2 more constraints to satisfy, so we cannot actually leave it, even though apparently I was able to get my alpha. That is extremely important to check this one as well. Again, 3, the I index is greater than the J index, so I have to use this first rule, and I have to replace J with 1 again, so it will give rise to exactly the same equation. Nothing new. So you can conclude exactly the same thing. Okay? But when it comes here, the index, the J index is now changed. But still, I have to use this rule because still I is greater than J. So I go to this and I replace J with 2. And then it means that I have alpha squared minus 2 times 3 minus 6 alpha. And then this becomes 8 equals to 0. I should also make this work. But then I can also factorize it. I think it's easier. Can you guess how should I factorize this time? I need two numbers whose sum is minus 6 and the product is positive 8. Minus 2 and minus 4. And then it gives me again two possibilities. Either alpha is 2 or alpha is 4. So choosing alpha 1 or alpha 2 satisfy, so make these two things happen, and then choosing 2 or 4 make this one happen, but I want all of them simultaneously happen. So what is the final answer at the end?
Alpha 2.
Alpha is equal to 2. So that's extremely important to realize that you have to continue even though you were able to find alpha in the first problem. Okay, and then we want to go to the next terminology, which is also extremely important in matrix theory, and then probably you can define it. That is the notion of a diagonal matrix. Even without me defining it for you, probably you can guess what is a diagonal matrix.
A matrix who has a diagonal.
No, a square matrix has a diagonal. So first of all, when I talk about a diagonal matrix, yes, I mean that it is a square matrix. But if you are a mathematician, which matrix do you define a diagonal matrix? That's what I'm saying. The reason that I am talking about this, because I think the names are reasonably good.
Oh.
Yes?
A triangular, no, a square matrix who only has numbers that aren't equal to 0 in the main diagonal.
Possibly non-zero numbers on the main diagonal. So in other words, can you complete it with the words upper and lower triangular?
I was just only thinking.
A matrix is called a diagonal matrix if and only if it is both upper triangular and lower triangular simultaneously. In that case, we call it a diagonal matrix. So a diagonal matrix, I can write it like this here. So for example, let me call it D this time for diagonal. And then I have a square matrix. So if you don't mind, let me emphasize that this is a square matrix, n by n. And then this term is D1. I don't know, this term is D2. And this term is Dn. I'm deviating a little bit about the notation. You can write D1, 1, D2, 2, Dn. It doesn't matter. But what matters is that these two are 0. All of them. But there is no restriction about what values you can choose with the main diagonal. You can choose non-zero values as well as the 0 value. So it doesn't matter at all. Okay? And then there is a symbol, simpler symbol for that. Some books write it like the diag of, only emphasize on the entries. Yes? So that's also another notion, yeah.
Did you write h times n?
No, that's n by n.
Could you explain why it's n by n?
No, if it's a square matrix, otherwise it doesn't matter. When you say a square matrix, it means the number of rows and the number of columns are the same. I have chosen them to be n. You could choose them to be m or whatever.
Could you not write n squared then?
No. So when you say a matrix 2 by 3, it doesn't mean 6. It means 2 rows and 3 columns. Yeah, that's the convention. So it's not a multiplication here.
Yeah.
Okay, so that's it. Let me see. Okay, so let me also, because I don't need to show the US style, I have written exactly the same thing here. And there is another terminology that you need to learn, and that's called a scalar matrix. So that was diagonal matrix. A scalar matrix is a particular case of a diagonal matrix in which all the entries are equal. So if you have every number sitting here to be equal, that is called a scalar matrix. So in a diagonal matrix, these numbers might be different, but if it happens that all these numbers are exactly the same number, then that matrix, of course, it is upper triangular, it is lower triangular, it is diagonal, but we have a particular name for them. They are called scalar matrices. Okay? So that is also something that you need to know. And there is one scalar matrix which is extremely important in matrix theory, and that is the case where all these entries are 1. Okay, and that's called the identity matrix. Okay, so if you have the situation that every entry, of course this is a very extreme case, this is 1 by 1, but this is an identity matrix, 2 by 2. Yes, this is the identity matrix, 3 by 3. Okay, and then this one, this letter is reserved for identity matrix, letter I. So I write I sub 1. It means this is the identity matrix of order 1. If I want to denote this, the symbol that I use is I sub 2. It means that this is the identity matrix 2 by 2. And that is I3, and then you can continue this list. So I can talk about an identity matrix, but if you specify the order, you can talk about the identity matrix, because the identity matrix of order 2 is only this one. So if I ask you, is this a scalar matrix, you will say yes, because all of these entries are equal. You will see that why this is important. This plays the role of identity in matrix multiplication. If you take a matrix and multiply it by the identity matrix, the matrix will not change. So that's playing the role of 1 with numbers. Yes. So if I take a number and multiply it by 1, I will get the same number back. Then you will see that the matrix multiplication is defined in a way that if you take a matrix and multiply it by that rule that we will talk about that later, you will get the same matrix. So that's why we call this the identity matrix, because it acts like an identity. Okay, so it doesn't matter. So let me just show you the slides as well. So let's see. So we talked about diagonal matrix. So this is the form of a diagonal matrix, and this is the symbol that sometimes we use to show that this is the diagonal matrix, and that is a misprint. This 1 shouldn't be in bold. I will fix it later. And a scalar matrix is a matrix of this form. You see all these matrices that I have written are scalar matrices. Why this is a scalar? Because it is diagonal, but all the entries on the diagonal are equal. So you can, instead of that, you can write it like this. Instead of this one, you can write like this, and that's it. Yes?
Why was that a misprint?
The misprint? Yeah, because there is no reason that I put 1 in bold, yes? Yeah, because there is, when I write something in bold, it means that I am meaning something, I want to emphasize your attention, but there is nothing specific about that one. That's a misprint, I would say. Okay, and these are identity matrices. As I told you, these are identity matrices of different orders. Okay, I want to introduce you a piece of notation. You will see that this will be useful a little bit later when I want to prove theorems regarding matrices. Of course, yeah, it's a very handy tool, and Kronecker is actually a mathematician who actually invented this symbol. This symbol is extremely simple thing to introduce. It's called delta, Kronecker's delta. So delta, and then we have 2 indices, I and j. And then what happens? It is defined to be 1 whenever these indices are equal, and it is defined to be 0 if the indices are not equal. But of course, indices should be natural numbers. Yes? It's just a piece of notation. Okay. Yes? Question? No. So for example here, when I ask you what is delta 1, 2, you just, because 1 and 2 are different, you say it is 0. When I ask what is delta sub 2, 1, because again 2 and 1 are not equal, so you say it is 0. And when I ask you what is delta 1, 1, 5, 5, 9, 9, whatever like that I have written here, yes, all of them are equal to 1. Is that clear? So this means that delta mm is always 1, and it doesn't matter if you say delta mn or delta nm, because if m and n are equal, then both of them become 1, and if they are not equal, both of them become 0. Yes?
So is that a identity matrix then?
Yes. So it means that, yes, that's a good thing. Actually, that's the reason that it becomes important. So if I want to, I think I have addressed this later, so I will come back to it, okay? So one thing that I want to get used to this notation, there is nothing deep here. I'm just writing a bunch of numbers as matrices, and I have written some symbols there, and I ask you to calculate those symbols. That's it. There's nothing deep there, okay? So I have given you a matrix of this form, and I want you to calculate these sigmas. Okay, so we can go back and try to do it together on the board. Then I don't know how to. So let us just write here. So for example, let me keep the matrix here, and I want you to calculate this sum. Okay, so let me write the sum on the board. So let me name this. So it would be a long time if I want to write that matrix here, but let me just write the sum and switch the view and then try to do it together. So k equals to 2 to 6, and then I have written here a sub 2k, and then I have delta, which is the Kronecker delta k sub 5. Okay, now let us try to calculate this. Of course, I cannot show you the matrix simultaneously. but if you have your laptop, you can put the PDF file in front of you so that you can also see it. Okay, so let me now change the view. But before actually doing that, I want to forget about the matrix, whatever it is. I want you to expand this sigma. So let us see what happens. If I expand this sigma, how many terms will survive, do you think? If I expand this sigma, first of all, how many terms will be when I open up the sigma? K is 2, then 3, then 4, 5, and 6. So there will be 5 terms, yes? So if I open it up, it will be 5 terms. But how many of them will survive at the end because of the presence of that delta, chronicle delta? So let me open it up. Might be you're confused. So if I ask you to open it up, what is the way that you have to do? You replace the counter. These are the same letters. You have to replace the counter with the first number and then do the same thing for the next number and until you reach to the final limit and then add those numbers. Yes, that's the way that we do it. So this becomes A 2 2 delta 2 5, and then what happens for the next one? A 2 3 delta 3 5, and then plus A 2 4 delta 4 5, and then you have A 2 5 delta 5 5. And then finally one more, yes? A26 delta 5 6. And I think if you understood what is the meaning of that piece of notation that I introduced, you see how many terms will survive? Which term will survive? Because delta 2 5 is 0. So I really don't care what is the number. I even don't need to look at the matrix to find this one. Yes?
So only if they're equal becomes 1.
Yeah, exactly. So this means that this term is 0 because 2 and 5 are different.
Yeah.
So I don't care about this part. So it's 0. So which one will survive? Do you agree what I'm doing? And then this will survive. So what is the value here? 1. So what matters for calculating this is just one entry in that matrix. So this means that this is A2 5. And I want you to understand, don't write it down. I want you to do it fast after understanding. So it is extremely important. So what is the role of the sigma, delta? The delta, if it has an index, which is the counter, it will kill the sigma. And then you replace the index k everywhere with the second index of delta. So you see it happens. What happened? So if you see a sigma with delta inside in this form, you can imagine that delta and this sigma are gone. The only price that you have to pay is to replace the counter with the second index of delta. So this is why I changed k to the second index of delta 5. I don't want to make it hard for you. Learn it as you like. But the important thing is that I don't want you to every time expand it and simplify it. I want you to understand that under 1 second, you should be able to write that this sigma after expansion becomes A25. Is that clear? Okay, so and then of course, if you want to answer that, you should go back to your matrix. And see where is it? A in the second row and in the fifth column. So I go to the second row, 1, 2, 3, 4, 5. It is a 1 here. So the answer to this finally becomes 1, yes? So the answer to that becomes 1. Okay, I can wait a little bit for you so that you can solve this second one and the third one. I just want to get used to this sigma notation, because if we want to prove theorems in matrix theory, if you want to accept them as a fact, of course we don't need these details, but if you want to prove things, it's good to know about them. So I want to wait for you so that you can calculate these two for me. And then write this as a number so I can understand. Okay, could you solve that? Yes, what's the answer to the first one? 0, yes. Because, you know, in order for this delta to be 1, k has to be 7. but k will never ever reach to 7 because the final limit is 6. So it means that you really don't need even to calculate anything extensively. You just answer 0. But you need to understand why. What about this? This is possibly not 0 because the second index of delta is 3 and 3 is in this range. So at some point k becomes 3 and that term will survive. But something is important. If you learn what I told, the way that I do it, I drop this delta with the sigma. Yes, because of what you understand. If you don't want, you can extend it, but don't do that. Try to understand it quicker. So I will drop the delta with the sigma, including that counter. But the price that I have to pay is in what is left. I have to change every appearance of k to the second index of delta. So it means that I don't know how do you want to think about it. This is the way that I think, but I immediately write this. So I just want you to understand. In any way that you want to think, it should be very easy for you to write immediately this expression. Is that clear? So I drop delta, and if you want to imagine, it means that I have to put k equals to 1, but k1, 3, this delta will cancel out. k2, so the only thing that survives is that when I put k equals to 3. But when I put k equals to 3, this becomes 1, so this means that I have put k equals to 3. Okay.
But how can you drop the two?
No, I just say that this means this.
So
I'm not saying that this is the mathematical way of doing it. In my head, I think that this works in this way. But you should be able to expand it and see that there is only one term survives.
So it's a shortcut.
Yeah. It's a shortcut of doing that. That's what I'm saying. I'm not saying that this is opposite of this and they are canceling out. No, the way that I think to do it faster is to do this. Otherwise, in your head, you expand it in your head. Only the term where k is equal to 3 survives. So then you drop that. Yes? And then, of course, you can go back and read this entry from the matrix and then replace it with a number. What was the number you got? Anyone got the number? So we have to go back in if you want to do this. So we have to go a little bit back. Let me see. So what are the numbers? A1, 3. On the first row, third column. So this is this one, yes?
Squared.
So that is 2.
You square it after you find the number.
Pardon?
You square it after you find the number.
Yes. So that was 2. So then it becomes 4. Let me write 2 to power 2 plus 2 times 2, which is 8. So the answer to this is 8. Any questions? Yeah?
Yeah, in an exam or whatever, if we're given a sigma which we need to calculate, we don't always need to write it out and expand it, or do we need to expand it if we want to show how we solve it?
I will talk a little bit about sigmas today to make it a little bit fun today. But I mean, sometimes you have to open up the sigma unless you are very creative to find the shortcut.
Okay, but if
Yes.
if I can explain the shortcut, then I don't need to expand it.
Yeah.
Okay, so like this, because we know this.
No, in this case, I also prefer you to be able to write this one
So
immediately.
since we can skip a lot of
Yeah.
expanding, then if you would just explain.
Yeah. If it contains the delta, that's actually the whole thing. Yeah, you're right. Okay, so now let me see what is now we have here. So we learned about this one as well, and that is what Rocco actually told. So that is one reason that this delta symbol is important. So if I give you an identity matrix, and if I ask you what is the entry of the identity matrix sitting on the ith row, jth column, it is exactly the chronicle delta ij. Yes. So let me go back to the board. So here you see that here I can say that this identity matrix 3, the entry on the ith row, jth column, do you agree that if I want to write something, I can immediately write the chronicle delta in front? Why is that? Because if I and j are equal in this matrix, you see that the entry is 1. And that is happening exactly for delta. If I and j are equal, delta is 1. So that is correct. But if I and j are not equal, it means that either I am here or there. You see that the entries are all 0. So this means that, okay, yes. So what can I write here? If I is not equal to j, delta, chronicle delta becomes 0. Yes? So for example, can you write this? If I give you a scalar matrix, say 2, 0, 0, 2, 2 by 2. If I ask you, can you write something for this entry, the matrix A sub ij? Can I write something in front of it in terms of chronicle delta? What can I write? I can, yes?
Would it be 2 times?
Yeah, exactly. So it becomes 2 times the chronicle delta. Yes, why is that? Because if I is equal to j, you see that you have 2. But on the other hand, if I is equal to j, this symbol becomes 1, and you multiply it by 2, it becomes 2. So that's correct. If I is not equal to j, entries are 0. On the other hand, if I is not equal to j, this is 0, and multiplied by 2 is again 0. So you can also write the scalar matrices in this form. Yes?
Why is I and j outside of the
So I told you that we have different notations. Please read the lecture notes, okay?
Yeah.
So I told you that sometimes when I write A, I refer to the entry with this small letter.
Yeah.
But sometimes I want to keep the name of the matrix. But of course I cannot write something like this. Then I put a pair of brackets around that, meaning the same thing. So if I want to mention the i's and j's entry,
Yeah.
I either show it in that way or show it in that way.
Okay.
Yeah. Okay, and then another piece of information that will be important, I don't know if I can cover that part of linear algebra that this notion becomes important, but it doesn't hurt if you know that, and that is the notion of the trace of a matrix. Okay, so if I have a square matrix A, the trace of matrix A, which is denoted by this symbol, TRA, is the sum of the entries on the main diagonal. Yes, so that's the definition of the trace. I don't know if we can cover that part of linear algebra that shows that this is important, but at least I will give you an example that the notion of trace will become very, very useful, even at this level. Okay, so what is the meaning of the trace? So if you have a matrix A, which is Aij, n by n, it should be a square matrix, otherwise I am not allowed to ask you what the trace is. So the trace of this matrix means the first entry on the main diagonal plus the second entry on the main diagonal, and then continues plus the last entry on the main diagonal. So you see that I have written 1, 1, 2, 2. It means that I am adding the entries. And if you want to write it as a sigma notation, so you can write sigma, and then you write A sub I, but again I, because all of them have the same indices. So it means that now I goes from 1 to n. So that's the notion of the trace of a matrix. Okay. So for example, can you tell me what is the trace of I3? What is the trace of I3? This symbol. I told you that this letter is reserved for the identity matrix 3 by 3. Just say it.
3.
It's 3 because I start adding these numbers up and I reach to n. So in principle, can you tell me what is trace of IN? IN means the identity matrix n by n. Yes?
N.
It's n because I am adding one after the other, one after the other. So it becomes 1 plus 1 n times. So this becomes n. So I will write some examples that it's good to know about the trace, but you might say why this is important, why the sum of the entries on the main diagonal happens to be important. Hopefully I will be able to cover that part to answer this question at least partially. But definitely I will give you an example that you will see that the notion of trace is extremely important. Okay. So that was actually the first part that I wanted to cover, and I have written some examples and problems. I don't know, have you checked them out? You were supposed to do some of them. Yes?
Is it AA? No, sorry, II.
I
Sigma?
yes,
Yeah.
because all of them have the same indices. Okay, so let me. I think it would be good if because I started talking about sigmas, and sigmas are important in this course. Let me try to practice a little bit another very important rule of sigmas so that we can actually we will need it later a little bit. Okay, so let me pause recording here. Okay, now actually let us the matrix theory be at this stage, and let me just go back and review a little bit about sigmas. So we already talked about sigmas. So for example, if I ask you what is this one, can you calculate it for me? Sigma minus 1 to power k, I would write k goes from 1 to 100. So what's the answer to this sigma? Yes?
Would it be minus 100?
Is it? Yes? No? Yes, I think it's 1. No, it's not 1. No? Might be I'm confused, yes? How many terms are there?
101.
Why do you say 101 this time?
What is
It starts from 1 up to 100. How many terms are there?
Okay.
100, yes?
Okay.
And then one of them is positive 1, the other one is negative 1, so they cancel out. So the answer should be 0. Yes or no? So let me see. If I open it up, what is the first term? Minus 1 to power 1 plus minus 1 to power 2. And then I will continue minus 1 to power 100, yes? So this becomes minus 1 plus 1 minus 1 plus 1 until plus 1 at the end. But how many plus 1s we will have? 50. And how many negative 1s we will have? 50. So they will cancel each other, and then I will get 0. Yeah, so that's easy. By the way, it's also good to see how GeoGebra works with sigma. It's good to know about that. So let me just go to GeoGebra. And I think we go to CAS view here. And I think it's better to get rid of this algebra graphic view so that we have a bigger board. Okay, so what you do, you just write sum. Okay, and then you go here to this expression variable start value end value. So that is the sigma. Okay, so that is the way GeoGebra knows about sigma. I don't see any sigma notation somewhere here, but this is the way that I could see. So if I want to write that, so I would write minus 1 to power k, yes, and then I go down, and then what is my variable here? That is the counter of the sigma. So I introduce that is k. The starting value is 1. The final value is 100. Yes, hopefully it's 0. So this sum is 0. So that is the way that you do sum in GeoGebra. Okay. It's good to know the software. Okay, it's very good to be quick. And then, if you found something interesting, please let me know. It's always good to share things. So I go back here on the board. Now today I want to talk about something. I remember I was teaching you this when you were in the first grade, and that was the telescopic sum. I'm sure that I mentioned that word, but might be you have forgotten. But that is important to understand it now. So let me start with a motivating example, and then I'm sure that I solve this example for you. Okay. So I give you this sum, 1 over, I intentionally write it 1 times 2 plus 1 over 2 times 3, and then I write plus 1 over 3 times 4, and then I will continue this list. At some point I reach to 99 times 100. So if I ask you, this is a strange way of writing things, but this is 1 over 2, this is 1 over 6, this is 1 over 12, and then it continues and I reach on 1 over 9,900. My question is that without using calculator, what is this sum? Okay, so we want to calculate this. So how should I do that? I just want to solve the problem for you because we do not have that much time. And then I try to teach you now a little bit better way to do it. Because in the first grade when I was teaching you this, I didn't use the notion of the sigma. I just described it for you. So let me just tell you, and then instead of 1 over 2, I can write 1 over 1 minus 1 over 2. Agree? This is correct. Because this is 1/2 and this is 1/2. But why I have written it in this way, you will understand shortly. So 1 over 2 times 3 is what? 1 over 2 minus 1 over 3. Do you agree with that? Yes or no? Because 1 over 2 minus 1 over 3, if you do it in your head, it becomes 1 over 6. And that's exactly 1 over 6. Yes? And then if I write 1 over 3 over 4, I will actually try to prove it. I want to ask for you, how do you know that this model will continue until I reach to that point? Okay, so I can write it 1 over 3 minus 1 over 4. So that is engineered in that way. So if you calculate 1 over 3 over 1 over minus 1 over 4, the common denominator is 12. 4 times minus 3 times, which is 1 again. So I will get this back. So what I'm writing is correct. And then I can continue this list until I hit the very last one. 1 over 99. Might be this is a little bit harder, but I hope that you can convince yourself that this is still true. Do you agree with me that this is also true? Because the common denominator is the product, and then 100 times goes here, minus 99 times goes there, and then if you subtract them, it becomes 1. That's also true. But usually in these dot problems, it is extremely useful to guess the previous term. What's the previous term that I haven't written down? What is that? Every 1 contains a 1.
98
yes,
times
that's
99.
98 times 99. Yes, that's good to write. So this means that when I continue this list, at some point I will reach to this, and then I can do the same thing. Yes? So this means that I continue this list. Okay? My goal is to find this sum S. So I have to add these numbers together, which was not easy. But instead of adding these numbers together, I think you understand that it doesn't matter if I add these numbers together. Yes, because they are exactly the same numbers. But what is the benefit? The benefit is that they will cancel out 1 by 1. So it's like a telescope that shrinks into a small. I don't know this. Have you seen this telescope? So it's something like that. So I mean that if you start adding them up, this term and that term will cancel out. This term and that term will cancel out. Is it possible that minus 1 over 4 is also cancelled? Yes, but with the one which is coming next, which we don't have it in our list. And then if you consider this 1 over 99 will be cancelled with that one, there is something here definitely which cancel this one out. And now can you see what is left? Yes?
1 minus 1 over 100.
Yes, so the answer to this is 1, which is left here, plus the last one, but the last one is negative.
So it's 99 over 100.
Yes, so it is 99 over 100. That's the exact value of this. Okay? So, and now if I want you to use Geogebra, either you should be patient to punch all these terms in. How many terms are involved? Immediately. 1, 2. How many terms?
100,
No.
101.
No.
20 million.
How many terms are involved there? When do you want to learn this? How many terms are involved there?
I give up.
So, no, you shouldn't give up. I look at here. This is 1, the first term.
Yes.
Second term, it is 2. Yes? So this is the 99th term. So there are 99 terms there. I don't know why you make it hard. Yeah, that's you need to understand it yourself.
Situations.
Okay, so I mean that the answer to this is 99 over 100. But assume that you want to test this idea using GeoGebra. How do you do that? This is where you need to know sigma notation. The first thing that I do, I will try to write this sum as a sigma. Okay, so Rocco, do you want to say?
Okay, well, should I just write out how the sigma would look?
Yes, just give me your answer.
Okay.
So you write this as a sigma.
Okay, so n would have to start at 1.
So you want to write n. If you don't mind, let me write k.
That's okay too.
Yes, k starts from
Yes.
1.
And k should go to 99. I think.
99. And
And
then,
it should be 1 over k times k plus 1. Is that right?
yes, this is, I hope that everyone understands that. So that sum can be written in this sigma form, yes? And if you want to use the Geogebra, so the only thing that you need to do, in Geogebra I wasn't able to find a sigma like this, so I just write sum, and then what do I do for my expression? I put this expression in, and I have to introduce the variable, because it might happen that you also have another variable in the sigma, but the counter is k, and the first value is 1, and the last value is 99. That's the way that you should be able to put it in Geogebra. So let us double check that as well. So I go here, so I would punch this sum, and then I have to find my expression. So it is 1 over k times k plus 1, and then I come here, my variable is k, the starting point is 1, the final point is 99, yes? And then I go there, and it's 99 over 100. So that is the answer that we get from GeoGebra. But what I want to teach you today is a little bit more efficient way of doing that. First of all, I didn't prove this mathematically. I relied on your intuition that this pattern continues for all these 99 terms. I just ask you, okay, you see the pattern, so we continue. But in principle, in mathematics, we should be able to prove it. One thing that I want you to understand in sigma, if you have a sigma and you have a counter k, it starts from some value, let's say m, and it continues until n. But only this type of sigmas. Inside the sigma, you have a difference, but it is a function f calculated at some point k minus the previous one. Something like this. So it is important. This, if you want to use this telescopic sum, what do I mean? This is a sum. Not every sum is called telescopic. Oops, I have to change the view. So not every sum is telescopic. Any sum, so that inside the sum you have the difference of two functions calculated at consecutive values of the counter. I don't know how to explain it, but when I give you this example, you understand what I mean. So this is a telescopic sum. This is also a telescopic sum, you know. I write a sigma, k goes from m to n. I can write some a, for example, in matrix theory, sub k plus 1 minus a sub k. That's also a telescopic sum. Yes? So when I say telescopic sum, it means that I have a sum sigma notation. Inside the sigma notation, I have the difference between two terms that depend on consecutive values of the counter. Is that clear? So k plus 1 and k are consecutive, one after the other. K and k minus 1 are also consecutive. If you face such a sigma, it's extremely easy to answer it immediately. What you do, you take the one which has the higher counter. Between k minus 1, k is bigger. You replace this bigger counter with the upper limit, so it becomes f of n, and minus, you replace the lower counter with the lower limit, f of n minus 1. So if you are patient and open the sigma up, only these two terms will survive. And that is clear, isn't it? What I'm supposed to do? First, I have to put m, so this becomes f of m minus f of m minus 1. Do you agree? And if I go to the next one, what is the next one? The next one is k equals to m plus 1. So this becomes f of m plus 1 minus f of m. Do you agree? The next one is f of n plus 2 minus f of n plus 1. And then this list continue until I reach to the last one. And again, the same story happens. What is happening? This and that are cancelled, this and that are cancelled, this one and the next one will cancel, only these two terms will survive. So the idea is exactly the same. Okay? Now, why this is a better way to do it? Because if you give me this, k goes from 1 to 99. By the way, whenever they are asking you to calculate sigmas with a lot of terms, this is the only trick. Otherwise, there is no other trick, so you have to calculate everything. But if I give you this and you are a little bit smart, but after being experienced by some of these problems, instead of 1, I write k plus 1 minus 1. First of all, do you agree that, sorry, the k plus 1 minus k. Do you agree that this is 1? Yes? And then I write k over k plus 1. And what I do, let me just be patient and write everything in detail. I take this one and then divide it by this. Minus, I take this one and then divide it by this. Yes? And then what happens? This becomes sigma, k goes from 1 to 99. K plus 1 and k plus 1 are simplified. It's 1 over k. And then k and k are simplified. This is 1. Yes. Now you see, I changed this sum to a telescopic sum. I want you to train your eyes to catch the pattern. Do you see that this is a telescopic sum? Why is that? Because inside the sigma, first of all, I have a difference. And then I have the same thing which depends on consecutive values of k. So your function is 1 over x. This is f of k minus this is f of k plus 1. Any way you can convince yourself. I don't want you to write these details, but I want you to train yourself to immediately realize that that's a telescopic pattern. It's a telescopic sum. Is that understandable? Okay, and then whenever you have a telescopic sum, calculating the sigma is super simple. What you need to do, you need to replace the counter. This is the lowest, this is the lower counter. You replace it with 1 minus, this is the higher counter, you replace it by 99. So it becomes 1 over 99 plus 1, and that's exactly 1 minus 1 over 100. Yes? I actually tried to explain everything in detail. You might think that this is faster, but I would say that if you learn and practice a little bit more, you will understand this is extremely efficient. This is an extremely efficient method. Is that clear? So this is not something that you can immediately work out, but I have to give you a lot of examples so that you can learn this trick. For example, let me ask you this question. What do you think about this sum? Sigma k goes from 2, so let me see, what is that? K goes from 2 to 999 logarithm of 1 plus 1 over k. Okay, so for example, I ask you to calculate this sum. How many terms are involved? This time I hope that you answer me correctly. How many terms are involved here?
998.
98. Because if I have started from 1 up to 999, there are 999 terms, but I have started from 2, so there are 998 terms. So I hope that you agree with me that if you want to calculate, you can use the Geogebra, of course, to calculate the final answer. By the way, we will check that one. But first of all, how can I do it by hand now? Without calculator.
Use the same formula?
No, but first of all, I told you that whenever they are asking you calculating big sums, there is only one trick as I know, and that is telescopic sum. So it means that that person who designed the question engineered it in a way that it becomes eventually a telescopic sum. Yes? and then you need to discover the pattern. You need to reverse engineer the problem. Okay, but how? Because this is some guide. For telescopic sum, you have to have a sigma, you have it here. Inside the sigma, you have to have a difference. This is extremely important to guide you what to do. This is a logarithm. 1 plus 1 over k is the argument, but it is not a difference yet. But if you have this in mind that you want to reduce it into the form of a difference, then I think you know what to do, and it's extremely simple then. Can you guide me how to make it as a difference? So I have to do something with logarithm. I hope that you remember something from logarithms. You're not totally by-minded, yeah? So let us work on this part. So I would say that logarithm of 1 plus 1 over k. Can you tell me how can I write this as the difference of two terms? So you need some revision, might be. This is the formula. Logarithm of x over y. Do you remember what can I write for this?
Wasn't it x minus y?
No, logarithm of x minus logarithm of y.
That's what I meant.
Okay, yeah. But I heard that you said x minus y. Okay, but this is the crucial point. Can you tell me how can I use somehow this formula to write this as a difference? Yes?
So you write log of 2 minus log of k.
No. I have to write this as a difference. This is not a difference yet. Yes?
A1 can be equal to k over k.
Yes? So you take the common denominator first. So you write k over k plus 1 over k, which of course means what? The denominators are the same, and then this becomes that. Yes? Yeah? Okay, and then what can I write? According to that formula, I can write logarithm of the numerator minus logarithm of the denominator. Okay, so then it means the question mark is equal to the sigma. K goes from 2 to 999. And then what you have logarithm of k plus 1 minus logarithm of k. Now, I hope that you agree that this is now a telescopic sum. Because first of all, I have a sigma. Inside the sigma, I have the difference of two terms. But what is crucial is these two terms depend on consecutive values of the counter. This is crucial. This depends on k plus 1. This depends on k. So that's exactly a telescopic sum. And then if I know the rule, I can simplify that. Now I want you to tell me what to do. I take the one with higher counter and replace the counter with the upper bound. So it becomes logarithm of 999 plus 1 minus logarithm, can you tell me what? I go to the one with lower counter and replace the counter of that term with the lower bound, which is, yes, and then of course this becomes logarithm of 1000 minus logarithm of 2. Logarithm of 2, I have to use calculator, but logarithm of 1000 is easy. What is that? It is 3. Yes? So because 10 to power 3 is 1000. So this becomes 3 minus logarithm of 2. So these 998 terms, if you add them up, at the end you will get 3 minus logarithm of 2. Yes? Is that clear? So that is actually important to understand. Okay, I will actually try to write some exercises for sigma as well, and then I upload them, okay, so that you can work this out. But before leaving, let us see if Geogebra is able to calculate this for us as well. So if I write sum, I don't know how to write logarithm in base 10 in Geogebra. So we come here. So I would write what? Log. Let us see how it works. Okay, so probably this is log base. Okay, just log. It works. Yeah. So log of which expression? 1 plus 1 over k. And then my variable is k. And then my starting point is 2. And my final value is 999. Let us see if Geogebra knows what to do. No, it is in trouble. Yes, because what GeoGebra wants to do, it really wants to calculate the terms and add them up. It's what I understand. Or is there something it shows that it is thinking? It's very strange. Oh, question mark. Okay,
Cool.
so we are smarter than GeoGebra, okay? But let us go to Wolfram Alpha. I think that guy is more creative. Okay, so let us see how it works. I have everything, and now we go to Wolfram Alpha and then try to check that one. Wolfram Alpha. Okay, hopefully, because sometimes you have to pay if the calculation is hard. But this is actually, I don't know the syntax in Matematik. I know probably this is some like this, and then you write log if I remember. But by the way, this is actually extremely, this is AI. You don't need to follow exact syntaxes. It tries to understand what you mean, okay? Hopefully. And then 1 plus 1 over k, and it always confirms that with you. I don't know. Let us use the GeoGebra syntax. But I know that the syntax in Mathematica is k, and then I write 2, and then I write 999, and then I close the curly brackets, and then I put it this way. It doesn't matter if you write it like this, but hopefully, if I haven't forgot. Anyway, you enter this one to see how it goes. First of all, okay. So that is immediately clear, but not in. So I hope that this also gives you the exact value. Why is that not? I was expecting that GeoGebra, this Wolfram Alpha.
form. You can click on
Yes,
exact
yes, exact form.
form. Ew.
No, but this is very strange. They are so stupid then. No, I'm completely sure they should be capable of doing it.
What is 3 minus log 2?
So no, that is exactly the correct number. But at least GeoGebra was not able to give the number. But here we have the number.
But the
So approximate form. No, the approximate form is this one. If you want, we can also calculate that one. So and then let me write minus. Let me see. I can give this number 3 minus log of. So let's just wait a little bit. I will come back to you. Okay. Now, if I ask this to calculate, my impression is that it should give you 0 or a number very, very close to 0. No?
Okay, Babak,
Yes?
the original approximation is incorrect.
Yeah, I
3
see
minus
that.
log
No,
2
I don't need to
is
say that to me
approximately
because I see that the difference should be 0.
Yeah,
Did we make any mistakes here?
I don't think so.
I don't see either. So 3 minus log of 2, and I have written this. No, that is very strange for me. Can you see if the flaw? Because
No.
I'm worried now.
Maybe it's not in base 10.
Yes, you are right. It is calculating in the natural logarithm. It's a very strange way. So I don't know. No, it is written logarithm. So their interpretation is logarithm in base 10.
I don't know.
You
It's
can
not,
test
it's not correct.
to see if it's based then or not by just writing something on it.
Yes, you are right. So let me just log of 10. No, it is probably correct. No, it is giving you 2. So this is ln of 10.
Yeah.
That is a strange thing. So how can I write logarithm in Wolfram Alpha then? Okay, might be I have to.
But doesn't that go against the conventions of math?
Yeah, that was a little bit strange. I don't know why Matematica has that convention that when they write log, they mean ln.
Try ln instead of log. Maybe they switched it.
No, that is not that stupid, probably.
Who
But
knows?
how to write log base 10 in Wolfram Alpha. So let us see if I can find something.
Maybe you just
It
write
says you
log
just
10.
write log 10.
Yeah.
No, but it didn't work.
You didn't write log 10.
Just log 10. Okay,
Yeah,
I have to
log
put
10
the
of-
log 10 here. Okay, so then let me see how it works. Because it was very strange that I could anticipate that GeoGebra will not be able to do that, but to be honest, I didn't know. So I just put a 10 here, yes? What you're saying. And then I would say 1 plus 1 over k, and then I have to put this one here as well. And then I would write curly brackets, k goes from 2 to 999. Yes. No, this. Do you think that I have done this time right?
Yes.
Yeah, that's the number. But now exact form, I don't think. But this is very strange. I really think that Mathematica is capable of seeing the pattern. The exact form, it doesn't make anything extra. No.
Could you try writing it in the other?
No, but
form?
let me see if there are some other information. No.
Maybe if you scroll down more.
So let me write this minus what the number we got is 3 minus
log
log base 10. What was the number? 2. Yes, and then this one, and then press enter again. It should be very close to 0. Yes. So there are some calculation or error. So it's 10 to power minus 16.
Why isn't it exactly 0?
No, because that's exactly clear. Because if you could see that this is exactly 0, it will give you the same answer. But
So for some reason.
so in
these
computer, it's 0. Yes, 10 to the power of minus 16. It means that the error that we are making is actually correct up to 16 decimal points. Okay. Anyway, but at least this was a stronger. I have the desktop version of Mathematica. I will definitely try this out because it is very good in understanding the patterns. Okay, but let us see what we can do. We can also work a little bit to find a way. So I mean that at least this shows that we are smarter than these computers yet. Yes. At some points. Okay. So one thing that I want to do is just I have updated the Google this one, so you can solve all the problems now which is left. I will write on and I will add one file for Sigma so that you can practice a little bit to increase your skills, improve your skills. Any questions? Okay, thank you very much. Yes, you have questions? No? Thank you.
Thank you.